Hi, my name is Dr. Michael Curry. I'm an associate professor at Tuskegee University, and I would like to welcome you to Tuskegee University and our research lab, where sustainability is our primary focus. And now that you have had a chance to study the word sustainability, why don't we venture inside and see some of the amazing research that's taking place in our research laboratories? Come on with me. Come on.
Hi, my name is Jasoria Floyd, and I'm a teacher at Booker T. Washington High School. This summer, I'll be working with the RET program, which is a research program for teachers in sustainable electronics. Today, I'm here with Dr. Melissa Reeves, and we will be discussing our summer research project. Dr. Reeves, will you please tell us a little bit about yourself?
Well, as you said, I'm Dr. Melissa Reeves. I'm a professor in the chemistry department at Tuskegee University. Been here for about 21 years, and my area of research is computational chemistry.
So what are flame retardants, and how are they related to sustainable electronics?
So flame retardants are different compounds that you can put into consumer products like clothing, furniture, and also electronic casings like plastic that goes around a computer or other electronics that prevent it from catching on fire if it would be subject to fire conditions. And so that prevents fires from spreading.
Okay. That seems like a pretty good chemical. So why is it considered harmful? Why would we want to not use those flame retardants in our everyday lives? Because they seem to be benefiting humans.
They do benefit, but unlike what people thought when they first started using flame retardants, they can come out of the consumer products and enter into people. And they especially found that in the 70s with children's night clothes, that if you dressed your kid in pajamas that had these flame retardants, after a few weeks, those flame retardants would be in your child. And they could find that through blood tests and other tests on the children.
Oh, wow. So with your research, how would we personally look at these different flame retardants, and how would your branch of research benefit society now?
Well, what we're trying to do is build models of the flame retardants, such as this one, which is triphenyl phosphate, in the computer and predict its structure and some of its chemical properties. And then we can use known data about how it affects different organisms to develop a rules-based method of predicting toxicities of other similar chemicals.
Okay. So Dr. Reeves, could you please explain the programs that we will be using to analyze the structure TPP?
Okay, so this is a structure of triphenyl phosphate that was originally built on the computer using a building program like McMoleplot. After building an initial structure, we submitted it to a program called GAMES, which is residing on a computer actually out in California, in Sonoma State University. And we ran a GAMES calculation to actually calculate the quantum mechanics of where all the electrons are, which gives us information about the structure, but also the chemistry of the molecule. Then we can download those results and resubmit them to another set of programs at the Virtual Computational Chemistry Laboratory, which, when we include additional data, can build a relationship between the structure of the molecules and their toxicity.
So this is not the same as actually going in the lab and doing hands-on research. This is more so computational science?
This is computational science, and it's helpful because we can do a lot more molecules and compare them to what is known about toxicity faster than you can go into the lab and test the toxicities, which usually requires large animal studies of different kinds of animals.
Okay. Sounds like a winner. I look forward to working more this summer.
Well, I think it's going to be fun.
Thanks.
Hello, I'm Shamar Huntley, a PhD student in Material Science and Engineering here at Tuskegee University.
Hi, I'm Shanae Jones, biology teacher at Sumter Central High School and RET student here at Tuskegee University. Shamar, why is your research so important to our environment?
Pollution is one of the biggest problems that we face today. A lot of the materials that we use actually end up in landfills, leaching toxic chemicals into our water supply, which leads to acid rain. Another issue is carbon dioxide emissions, which actually lead to global warming. So my research is important because I'm trying to find a potential solution, which in this case we're using cellulose, to make a lot of materials such as plastics more biodegradable as well as recyclable.
So why do different polymers have different structures and behaviors?
One reason polymers have different behaviors is the fact of its structure. So if you look at the HIPS, which stands for high impact polystyrene, you can see that it's in a pellet form. It's going to behave differently than the composite material. This is the fact that it has a different structure. Now, upon processing, we take this from a pellet form into a melted form, which kind of looks like this. As you can see, it's starting to melt. So the structure is beginning to change. That's why we're getting different thermal as well as mechanical properties from the pellet form to the composite form.
Hello, my name is Tequila Ross. I'm from Pasadena, California, and I'm a part of the RET program, which stands for Research and Experiences for Teachers on Sustainable Electronics. And I am working with Donald White. He is my mentor, and he's going to tell you a little bit about himself and his research.
Hello, my name is Donald White. I'm from Richmond, California, and I'm a master's chemistry student here at Tuskegee University. I'm working with nanocellulose and its implications on sustainability.
Hey Donald, so I know that we have been using this benchtop probe. Can you tell us a little bit more about it?
Yes, well, what we have here is a freeze dryer for short, but it's called a lyophilizer. And what it does is it takes your solid state, normally in aqueous solutions, that's in water, and it takes it from the solid state to a gas state without going to the liquid phase.
Hey Donald, so why should we care about that?
Okay, well, after we do acid catalyzed hydrolysis on our nanocellulose,
Right.
it's in an aqueous solution. And so we freeze it in the freezer for a negative 80 freezer for about 24 to 48 hours. And then we put it on here so that we can get dry powder, something that we can work with.
After you have successfully freeze-dried your substance, what's the next step?
Next step would then be to characterize. So we successfully synthesized and got a working product. And so now we would want to characterize that sample. And so we do that by using NMR. So here we have a 400 megahertz NMR. NMR stands for nuclear magnetic resonance. And it's the same technology as MRI, where instead of putting a person into a permanent magnet, you actually put your sample into a permanent magnet.
Oh, that's cool.
So after we processed our sample in the NMR, we actually get a spectrum. And that's what we have here.
Okay, so can you explain the spectrum for me?
Yeah. Okay, so basically what we take is relaxation times, where we take the sample and we put it in an applied magnetic field, right?
Correct.
And then we hit it with a radio frequency, which is called the Lamar frequency, which actually takes the spin of the nuclei and puts it into a different plane of symmetry, a different axis. So it goes from the Y down into the X. And the time that we're measuring is the time it takes to come back. It gives us a chemical environment, and it basically lets us know what we have, and this is what you have here.
Good afternoon, I'm Angelo Bedea. I am a physics chemistry teacher at Robert E. Lee High School, and I am here at Tuskegee University this summer participating in the RET program under the IGERT grant. I am here with Shatori Meadows. She is a PhD student here in the Material Science Engineering Lab, and we're here to do a demonstration for you guys today. So what are we doing here today?
Awesome, Mr. Angelo. Well, first of all, it's a pleasure to show you what we do here at the Material Science and Engineering Lab. Today what we'll focus on is natural reinforced composites. And I have some demonstrations here. Right here we have a carbon fiber. Now this type of fiber is being used within automobile industry, for example within the BMW industry, as well as we have natural fibers. Now this here is what we consider to be called a jute fiber. Now you may ask me, Angelo, what's the difference between the two, correct?
What is the difference?
Awesome. So synthetic fibers, what happens with these are they have a tendency to corrode or reduce a lot of properties. Well, they have high properties, but the problem with this is they have a lot of carbon dioxide emissions. Now, what that means is this carbon dioxide emissions actually affects the Earth's atmosphere, so we may wonder now why there's a lot of climate changes that take place. So what's the solution? Our solution is to switch to bio-based or natural materials, such as the jute fiber. And the jute fiber is actually derived from plants. So that's where we get our sustainability from. So the whole point of this is now, if we look at the carbon fiber, if you can feel this, it's actually heavy. Exactly.
Yeah,
So it's strong, but it's heavier. But take into consideration the natural fiber, it's actually lighter. So not only does the natural fibers give us the ability of sustainability, but it also gives us a lightweight material. So nowadays you see we're switching from the box cell phone that they used to have on Saved by the Bell to now we have a light iPhone or S7 phone.
Right.
So what I want to demonstrate to you today is how we make these composites.
Okay, real quick, 1 second. What is all of this stuff around the fiber? Like this one doesn't have it, but this one does. What is the
Awesome, great question. Now that's what's called epoxy resin. Now when we talk about a resin, we talk about a material that is an adhesive. It's more like glue. So it's found a lot in industry. It's mainly within paints and coatings. So we have here a sample of the epoxy resin, and it comes in two parts. This is your main part, and this is your catalyst or your hardener. So what happens is, once we add this catalyst to your main part, your reaction now is starting to take place.
Okay.
So it's an adhesive. Think of it like this. We bake a cake. I love to eat. You love to eat?
Love to eat.
I love to eat. So we think about it in the form of a cake. So we mix the egg, the dry batter, and the wet batter.
Right.
You have it together. That is your main part. Think of that to be your main part.
Right.
Okay? So think of this part to be the heat. So when we add this to this, as well as once we put that cake inside the oven, it now comes out into a solid form. That is how we get this solid fiber right here. So we look at more of the resin, again I said as an adhesive. Another example I can give you, think of the fibers when we use it with the fibers. We think of the fibers as being the bread, okay? We think of this resin as being the peanut butter.
Okay.
So my demonstration to you today is show you how to apply the epoxy resin, which is essential as an adhesive to the fibers in order to make a natural reinforced composite. And these can be used in a wide range of applications, including electronics.
Okay, so naturally, before you do all of the stuff you just talked about, baking the cake with the epoxy, with the resin, this is what a natural fiber looks like.
Correct.
This is basically a burlap sack or potato sack or something like that.
Exactly.
This is naturally biodegradable.
Awesome.
So this is very, very good compared to your synthetic carbon fibers, which are very stronger, have better properties, is what you're saying. But how do you make this? How do you get this out of the earth?
Now, carbon fibers are basically, just as they say, synthetic fibers. Anything with synthetic just adds the use of petroleum byproducts.
Okay.
So it's fibers like any fibers on our clothes or anything that we wear, it just has the addition of petroleum byproducts.
So you're saying oil, petroleum like oil. You're saying crude oil?
Crude oil.
Okay, so that's why it's bad for the environment.
Exactly.
Because to make this, we have to destroy more of the planet to get this made for our cell phone to be lighter.
Exactly.
Okay.
So then we come with the solution. Why not go to a more bio-based aspect of things? We can naturally get these from plants.
Okay.
The only thing with this is because it is natural fiber and it comes directly from plants, we have to treat the fibers.
Right, with the epoxy and the resin.
Correct.
Okay.
And also with some other solutions. Now, why do we treat the fibers? Again, we're taking this from plants. So it tends to have some type of impurities or some dirt that is on the fibers. So what we want to do before we use it, we want to make sure we remove any dirt as much as possible that can increase our properties.
Okay, cool. Makes sense. So what are you going to do? Are you actually going to do something for us today? Or
Yeah, I just want to show you a simple process of how you go ahead and make an epoxy composite. Now it's called a composite because it's made up of two or more components.
Okay.
The fibers will be our first component, and the epoxy resin itself will be the second component.
Okay.
So what I do is I add the part B, which is again, take for example the heat from the cake. This is our heat, and I add this to part A, which would be our batter of the cake. So what we do is we mix it together for a period of time until it's well blended and homogeneous. Once that is completed, we end up with a solution similar to this. So what we do now is we add the epoxy resin to our fibers. Again, I said it's like a sandwich layer. So we add the epoxy resin to our fibers and be able to spread it around. Now you want to get as much epoxy resin over these fibers as possible. Again, we want the adhesion between the two to be very compatible as well as to stick so that we have more of a strong material. So again, 5 at the bottom is our first slice of bread. Love to eat. The resin, this is our peanut butter.
Right.
And now what we do is we apply it with our second slice of bread.
Right.
Now the key thing to making a composite is you want to apply pressure as well as, again, temperature to your resin system. And I'm going to lift this up. As you can see, we have some wet part and as well as we have some dry part. Now what we want is we want to press this out so our material looks completely wet.
Right.
So I'm just going to go ahead and apply some more pressure to it.
Just move it all around.
Just move it all
I
around.
would not eat this sandwich.
But
Touching it too much.
exactly. But in this department, we call this method that we're doing a hand layup method. So it's simply just using your hand, more of using a ruler pin to apply to press. And as you can tell the difference from what I showed earlier, we've now submerged most of the fibers of the resin.
Right.
So what we do is we let this sit for a little while, and again, we get a composite that looks similar to this.
Wow.
Now, one key to this is you have to apply pressure to it.
Right.
So again, if we have a stack of books, it's like a grilled cheese sandwich now.
Okay. A panini.
Exactly. There you go.
Got it. Thank you.